So hopefully the assignment went okay. I didn't get too many panic emails, so I assume that it went fairly well for people. If you have any issues with that, I'm gonna be a little bit flexible with this first assignment if there were issues, so do let me know. But with that, we're gonna transition from probability into what we really want to do with that probability, which is to study stochastic processes. So this begins the second topic of this course, which is on stochastic processes. So let's start by actually talking about what a stochastic process is. It is a sequence of random variables, x of t, where the index t So the index t takes on the meaning of time. So we interpret it as a dynamical random variable, or how a random variable changes from time point t to time point t plus 1. And so because we are talking about a random variable, we have a state space. So it's conceptually exactly the same as the state space for the random variable itself. So it is the domain of the random variable x. Okay. And the index t can be either discrete or continuous. So I'm going to pause there for a second. So time here is interpreted, or is t. So how can we have a discrete time? So hopefully you guys have talked about discrete time models before in a previous class. So when we talk about discrete time, what situations might I have a discrete time in? I mean, it seems kind of weird. Like time is naturally continuous, right? Like there's milliseconds and femtoseconds. So how can we have a discrete time? Ah, thank you, Ananga. Exactly. So if we're measuring data on a discrete interval, like we measure the data every single day or every single week, then it's natural to measure time in the units in which we measure it. Is there other reasons we might have discrete time? Yes, Mark.
Like maybe certain species kind of have like this sort of cycle to their life where like they're all kind of dying around the same time and new ones are born.
You're exactly right. I don't think I spelled that right, but synchrony in the life cycle. So if there's some sort of periodicity where we have to naturally measure events occurring on a unit of a season or a year, then we should model in discrete time. And the third option is just as a counter of events. So sometimes events are actually occurring in continuous time, but we don't really care about that time dimension, and it adds a lot of complexity to talk about that time dimension. So sometimes we just want to make things simpler by actually counting events rather than counting the amount of time that occurs between them. So we can simplify our problem if we don't really care about the time dimension. All right, so that's what it means to have a discrete time space, which means that we end up with a whole set of stochastic processes that fall into this kind of diagram. So you can have time either be this discrete time for several different reasons, or you can have continuous time for all the other reasons. And then the outcome of the state space, just like we have a discrete and continuous random variable, we have a discrete stochastic process and a continuous stochastic process depending on that domain of that state space. So today what we're going to do is we're going to go through each of these boxes and talk about one particular example in each of the boxes. So I'm just going to list these here to begin with. So for a discrete time, discrete space stochastic process, one example of this is a branching process. Okay, so let's talk about one example of a branching process. So yeast, or Saccharomyces cerevisiae, there's lots of different types of yeast, but the one that I'm going to talk about today is Saccharomyces cerevisiae, which is brewer's yeast, which is what you naturally use in brewing. And so it is also called budding yeast because it reproduces by this budding of the yeast. So the parent yeast creates this little nodule on the side, and then that nodule will eventually become a second yeast cell. And so we could imagine that any one yeast can have two different things. It can bud with probability B, or it can go extinct or die with probability 1 minus B. All right, so here, our state space, we might be interested in the number of yeast cells. So this would be important for knowing whether or not our process will eventually ferment our brew. And so the state space is the natural numbers. And time here, at least for the time being, is going to be counted in terms of the number of budding events or the number of events. So either budding events or death events. And so it is also a natural number. Note that these budding events and these death events actually occur in time as well. And so we could also consider the time over which these occur. But for right now, let's abstract that time and really focus on whether or not these events occur. So in this case, the resulting stochastic process, we could look at this graphically. And we could kind of plot out our stochastic process graphically in the following way. So one way of thinking about stochastic processes is that you take your state space and you write your state spaces as a bunch of different bubbles. So here we could have 0 yeast cells, we could have 1 yeast cell, 2 yeast cells, and so forth. So this could go off to infinity. So obviously we can't draw it off to infinity, but you could imagine having all these events out to infinity. So this little diagram wasn't originally included in my notes that I posted online, but I've updated them this morning. So if you have an old version of notes and you're like, where did this figure come from? Just go look at the more recent notes. So you could imagine drawing your state space as these bubbles. And then we're going to write the probability of transitioning between these different bubbles with the blue arrows. So we have the probability that that 1 yeast cell dies with probability 1 minus B, or it could bud with probability B, in which case it becomes 2 yeast cells and so forth. And so we end up having this process. And if we were to plot the dynamics of this process, it would look something like this. Oops. So on this axis, we have some measure of that discrete time. So generations, for example, if we count one generation as one event, or you could relabel this as events. And then on this y-axis, we have the number of yeast cells, and we have a bunch of dots. And what this outcome is it's called a sample trajectory. So if we were to run this again, we would end up with a different series of dots, a different trajectory. So each trajectory is a random draw, or it's stochastic, and hence the word stochastic process. Are there any questions about this example. All right, so we'll talk about branching processes a lot more, but I wanted to give you an example of a discrete time, discrete space stochastic process. So let's keep going. And let's talk again about discrete state, but in this time, talk about continuous time. So one good example of this is called a birth-death process. So just like I mentioned a moment ago, this counting events is kind of hokey, right? Those events are actually occurring in time. And so if we care about that time axis, the corresponding model is not a branching process, but it's something called a birth-death process. And instead of using yeast, I'm going to use the case of an infectious disease. So we might have something that looks like this. So hopefully you guys have all seen something like this before, which is a flow diagram representation of a differential equation. And this is specifically the SIR model. And hopefully all of you saw something like this in 155 or somewhere else, where you have the number of susceptible hosts, the number of infected hosts, and the number of recovered hosts. And for today, we're going to be really interested in the number of infected hosts. So this focal variable is I. So if we think about what can happen to I, you can have bursts of I, so creation of I, that occurs at a density, a per capita rate of beta S. So we have this birth rate lambda, which is per capita. So the total rate is lambda times I. And similarly, if hosts recover at rate gamma, that is their death rate. And just because of classic notation, we'll call the birth rate lambda and the death rate mu. You could use any variables that you want, but I'm just going to stick with the classic notation. So you have these two per capita rates. So we could draw the corresponding stochastic process in the same way that we did up above, where each of those states is now a bubble. So you can have 0 infections, 1 infection, 2 infections, all the way up to an infinite number of infections, or the size of the population. But instead of representing probabilities on these arrows, we're going to represent rates. So we have the rate at which 1 individual dies, the rate at which 2 infections die, 3 infections, and so forth. And so you have rates on the arrows. Again, we'll talk about this in a lot more detail. At this point, I just want you to be able to think about different stochastic processes. Can anybody else give me another example of what could be a continuous time, discrete space stochastic process? Ah, great, the Lotka-Volterra model. So anything that has population dynamics, right? So the birth and the death of individuals. So you could have a deterministic Lotka-Volterra, and then you can model it stochastically with a birth-death process. That's a great example. All right. Now let's go back to our grid. In this category where you have discrete time and continuous space, you could have a first order autoregressive process. So in this case, that time being discrete is discrete because of how you measure it. So we usually think of autoregressive processes as something that's the result of data collection. So the example that you can think about that is very relevant in our current world is the sampling of wastewater. So wastewater is often used now to study the dynamics of an infectious disease. But if you're in a place like Vancouver, well, actually today is a great example. It's raining outside. Vancouver does not separate its like rain sewage from household sewage. So they get mixed up together. which means that the total amount of wastewater varies enormously from day to day. So if you want to know how much virus you would expect to be in the wastewater, you have to control for the amount of rainfall, or at least account for the fact that rainfall is going to lead to variation in volume. And so we could model the day of the year as our time axis as discrete, assuming that one sample of wastewater is collected every single day. And the total volume of wastewater could be given by our random variable x of d. All right, so what is a reasonable domain then for x in this case? Yes, Mark.
The positive real numbers.
Fantastic. The positive real number. So it's continuous. It can't be negative because you can't have a negative amount of wastewater. Now you could also normalize this x of d in a different way. So you could talk about the average amount of wastewater and set that equal to 0, and then count everything in terms of standard deviations in wastewater, in which case the domain would be the real numbers and not the positive real numbers. And one might be a much better model than the other and much easier to model. But for right now, if you just talked about the absolute amount of wastewater, then the positive real numbers would be a reasonable domain. All right, so in an autoregressive process, we can model the amount of wastewater on day D as some sort of function of the amount of wastewater on the previous day. So this is what we mean by auto. So the process depends on itself. So that's where the word auto comes from. And then I use the word first order. And the first order comes from the fact that the day D depends just on day D minus 1. Plus some error. So you have some deterministic function and some noise, and that's what makes it stochastic. All right. If we were to look at a sample trajectory from this kind of stochastic process, it might look something like this. So you have the relative concentration of wastewater on a particular day, and it can vary continuously. It's usually around 1, so this is a relative amount, and it varies from day to day, and you measure it once a day. Any questions about this? All right, one more process, the very last one. A good example of a continuous time, continuous space stochastic process is Brownian motion. So does anybody know where Brownian motion comes from? Like what motivated Brownian motion originally? Has anybody heard of this before? Okay, Rennie, I see you nodding. Would you be willing to vocalize where you've heard about it before?
It's the motion of a particle in a fluid, right?
Amazing, yes. So it was originally motivated by physics and the stochastic movement of a particle in space. So it could be a fluid or it could be the fluid of air. But since this is a biology class, I'm going to give a biological example of Brownian motion, which is the evolution of a neutral, and I'll talk about what that word means in a second, phenotype or trait. All right, so let's unpack this. So it's the evolution of a neutral trait throughout a phylogenetic tree. So here's an example. So phylogenetic trees are little graphs that tell us about the relationships between different species. So we have 3 different species here. An example of this would be a chimpanzee, a bonobo, and a human. That's something that we're all kind of a little bit more familiar with. So you could have some relationship between these different species. And we could take some trait, some characteristic of apes that we're interested in, and we can make the assumption that it's not under natural selection. So it's just evolving randomly. There's no driving force that's driving it one direction or the other. So that's what it means to be neutral. It's not under natural selection. And so we can imagine that the ancestor had this phenotype here, and then it starts evolving randomly amongst chimpanzees, and it starts evolving randomly amongst the ancestor of bonobos and humans. But once bonobos and humans diverge, it starts to evolve independently in the 2 of those. So this is a model of Brownian motion, and it gives us our null expectation or our neutral expectation of trait evolution. So it's a very useful model for testing whether natural selection is actually occurring. All right. Any questions about those different stochastic processes? Again, we'll talk about a couple of them in much, much more detail until you'll wish we weren't talking about them anymore, but this is a good overview. Okay, so let's ground ourselves with a few more definitions. The first of these is the fact that we're going to only consider stochastic processes in this class that have something called the Markov property. So verbally, what the Markov property means is that the future state depends only on the current state. One way that this is often talked about is that the process is memoryless. So it only knows where it currently is. It doesn't know how it got there. Another way that I like to think about it is that there is no inertia. So you have a position, but you do not have any velocity. So there's no velocity pushing you in one way or the other. All that matters is your current location. If we were to find this mathematically, we have that the probability that the state at time t or n plus 1, and notice that I use different letters here. You've probably caught on to this. Sometimes I use t, sometimes I use n, sometimes I use d. It just depends on the application. So x of n plus 1 given x of n is equal to little x of n, and x of n minus 1 is little x of n minus 1, and so forth, all the way down to x0 is equal to x0. This can all be written simply as this. So none of these terms matter. We can ignore all of those terms. And this nicely helps us define something called the one-step transition probability. So the probability of going from state I to state J is given by the probability that we started in I and ended up in J. And our whole Markov process can be written in terms of these one-step transition probabilities. Note that you could totally rewrite this whole course from this point out, flipping these two indices. So often books will actually write this the other way around, which is the probability of going from I to J. But for convenience in this course and from now on, we will always use this notation because I find it easier to say. So it's the probability of going from I to J. So because of this, we'll end up using things like row vectors and right eigenvectors instead of left eigenvectors. But you could redo this whole course the other way around. So just keep that in mind. So when we have this is the probability of going from I to J. Okay. So the natural world is probably not Markovian. So the vast majority of the natural world is almost certainly non-Markovian. So as a little discussion, can you think of any things in the natural world that are clearly Markovian or clearly not Markovian? So transitioning from high school to university, as a Markovian process. So given that you're in high school, so there's weather, okay. Yes, so it's okay if the weather today depends on the weather yesterday. So let's unpack these two examples a little separately. Sorry, these are great examples. So I'm going to say that the transition from high school to university is pretty Markovian. So note that if you are in high school, the probability of you going to university is independent of whether you went from grade school to high school. Because yes, it matters whether you graduated from 8th grade, but this is saying, I know that you went to high school. So it's not saying that it depends on whether the probability that you went to university is probably not dependent on whether you went to grade school, high school, or grade school and high school versus just high school. So another way of writing this out is the probability of university given high school is probably very much equal to the probability of university given high school and grade school. How much you went to grade school probably doesn't matter. All right. So that was a great example. Now, weather can kind of fit into both camps. In many ways, we can often think about the weather tomorrow as just depending on what the weather is today. But if you've ever looked at like the precipitation map on your iPhone, you'll see that there's like a movement of a wave of a cloud or atmospheric river, as we discovered a couple of years ago. And so there is definitely a momentum to it. So there's certainly, weather definitely has a velocity. And there's a much different probability of rain today given 2 previous days of rain versus the probability of rain given just 1 previous day of rain and a question mark, right? So this is probably non-Markovian. But you have a very good intuition here that this weather, even though the weather tomorrow probably depends on, is better predicted by many past days of weather, we can probably just change our model to approximate it very well by just knowing the current state. So oftentimes we can just change our model to approximate non-Markovian events as very Markovian. So we can often capture a lot of that momentum. So great examples there. All right. Any questions about what it means to have the Markov process property? All right, so let's go on to the next thing. So we're gonna also only consider processes in this class, except for maybe one example, that are time homogeneous. So this is the analogous thing to having an autonomous ODE. So we have that one-step transition probability. It's the probability of going from T, and I'm gonna write it a little bit different here. So instead of using a 1 here, I'm going to use a delta t, because that means this is the Markov property for both discrete and continuous time instead of just discrete time. So we have our little delta t here. And it's okay if this transition probability is the function of where we are currently, where we're going to, and how long it takes us to get there, but it is not a function of t. So it can depend on where you currently are, where you're going to, how long it takes you to get there, but not the current day of the year or the current time. Does that make sense, or that distinction make sense? So how much wastewater, or whether we go from rain to snow, can depend on whether it's currently raining. It can depend on whether we're trying to project whether it will snow or hail. And it can depend on whether we're trying to project 1 day in the future or 10 days in the future, but it can't depend on the fact that today is January 22nd. So it can't depend on the current time. All right. Any questions about that? It's a weird thing to wrap your head around. So take some time to just try to think through what would mean to have a time, what examples in the real world would be time homogeneous, and what examples in the real world would be time inhomogeneous, because only when we grapple with those things can we think about how weird this is. So take some time to think about those things today. And that brings us to our first topic, which is just talking about those discrete time. Discrete space Markov processes. Right. So notice that I snuck another word in there. I snuck in the word Markov because we're going to only be considering processes that have the Markov property. So as our first example, let's think about the coexistence of species in an ecosystem. So let's consider, I don't know, some ecosystem like a marsh. And this marsh can either have only species A. So two of my favorite species in marshes are liverworts and hornworts. So I'll just use those as examples. So imagine that here you have a marsh that's dominated by liverworts. And then you have state 2, where you have both species present. And a state 3, in which you only have hornworts. Okay. So we can use that same kind of technique that we just did before to model the dynamics of species coexistence from year to year. So imagine this is a temperate marsh like you often get here in the Pacific Northwest. So there's winter months and there's winter seasons. And so it's natural to think about what species reemerge in the spring. So you might have dispersal in the fall, and then you ask what species are there after the winter in the spring. And we can draw this with a transition diagram. To look something like this. we have a transition diagram. So we have these three different states, and we have transitions between them. So I've written these transitions in two different ways. I've either written them in blue as what you gain or what you lose. So here you're gaining species B or losing species B, losing species B or gaining species B. And in red, I have those one-step transition probabilities. Note that there's also a transition probability like this for every single one of those states, which is the probability that you stay in that state. So this would mean that in 2024, I have species A, and in 2025, I also have species A. So we have to think about how the process could change and how it could also stay the same. Make sense? Okay, so I'm gonna next take all of these red probabilities, all of these red transition probabilities, and it turns out we can nicely write them as a matrix. So I can write them as a transition probability matrix. So I have P equals the probability of going from one and staying in one, being in state 2 and staying in state 2, or being in state 3 and staying in that state, or going from 2 to 3, from 1 to 3, from 1 to 2, 2 to 1, 3 to 1, or 3 to 2. I'm saying those out loud because once again, I want you to just see these one-step transition probabilities and immediately interpret them. So if this is our transition probability matrix, we can represent the current state of the system as a current as a probability vector V of t. And this is going to be a row vector. If you defined everything in the other way around, it would be a column vector, but for this class, we're going to talk about the state as a row vector. And what this row vector is going to represent is it's going to represent the probability of being in a particular state at time t. So it's the probability that our random variable is in state 1, the probability that our random variable is in state 2, or the probability that our random variable is in state 3. All right, so by looking how V of t changes over time, we're looking at how a probability distribution changes over time. This is super weird. So if we run simulations, we get a single trajectory out. But what we want to model when we model a stochastic process is the whole probability distribution. So ultimately what we want is the probability of being in a particular state at a particular time. So we're trying to get out probabilities, not one trajectory. It's very useful to look at trajectories, and we'll do that a lot in this class. We'll simulate trajectories, but ultimately we want this probability vector. And I just find this a weird thing to wrap my head around, that you're trying to look at how a probability distribution is warping itself through time. Any questions about that? All right, so let's do an example. Let's assume that we have the following transition rate, or transition probability matrix. So this transition probability matrix would, for example, work in that coexistence example that I gave above. So we could interpret this as species A and B, and species B. Okay, so what is the probability that we go from having both species, so that was state 2, to going to having only species A? So I want to go from state 2 to state 1. What's that probability? Oh, sorry, I should say in 1 year. There's only a total of 9 numbers, so you have a 1 in 9 chance of getting this right. Completely random. Yes,
There's
Maddie.
answer in chat.
Oh, thank you. P21 is 0.4. 21 is equal to 0.4. Okay, thank you, Mark. All right, so that's that one-step transition probability, but we often are considering a whole set of outcomes. So let's consider an initial state where we say that the 30% of ecosystems, if we go out and survey ecosystems, 30% of those ecosystems have only species A, and 40% of those ecosystems only have species B. What does that mean for the probability of having species A and B? Yes, Mark.
It would be 1 minus the other 2 probabilities.
Fantastic. So we have a 0.3 here. Okay, so that's the first property that we have, is that we know if we sum over all of the different states of our particular state vector, independent of what time it is, it has to equal. And that brings us to some of the properties of a transition probability matrix. Need another page. Okay. So the first property is that all elements are non-negative. This makes sense, they're probabilities. So they actually not only are non-negative, but they have to be between 0 and 1. Second, the rows sum to 1. So the probability of going from I to J summed over all possibilities for J, where S is the state space, this has to equal 1. One way of thinking about this is you have to go somewhere. So even if that somewhere means staying in the same place, you have to go somewhere, so the total probability of going somewhere is 1. Now, the total probability of going somewhere else is definitely not equal to 1, but including those diagonal elements, which are the probability of staying in the same place, you have that equal to 1. There's several different ways of writing the following, but I'm going to write it in this way. So the probability of going from state I to state J in k steps, k units of time, is given by the ijth element of the k transition probability matrix. So this is called the kth transition matrix, or k-step transition matrix. And importantly, this is a matrix multiplication. Okay, I'm gonna pause everybody here. Please, none of you do p to the k, and that means that you raise each element of p to the k. Don't do that. This is matrix multiplication. This is a matrix power, and it means that you have to multiply the whole matrix by itself k times. It will not give you the same answer that if you raise each element of the matrix to the k. I guarantee you that either you or I will make this mistake at some point in this term, but we are going to try our very hardest not to make this mistake. So p to the k is a matrix exponential. Okay. Is that point clear to everybody? That multiplying matrices by each other is not the same as raising the elements to a power. Can I get some thumbs up from people? Okay, thank you. Good, good, good. Okay, now, because I guarantee you somebody will do this, and so I want to make sure that's clear. And then finally, we have something called the Chapman-Kolmogorov equation. And what this means is the probability of going from I to j in n plus m time steps is the sum over k, the probability of going from I to k in n time steps, and going from k to j in m time steps. All right, so what does this mean? It sounds really hard to write it out, but it's actually very graphically obvious. So if we think about all of the places we could go from I in n time steps, we have a set of possible outcomes, okay? So you might go from I to 1, I to 2, I to 3, and so forth. And then from each of those k, you'll end up going to j. You could go to j. And say we have that in m time steps. So the probability of going from I to j is the sum over the probability you went somewhere in the middle. You might have just gone straight from I to j and then stayed at j, but you had to go somewhere in the middle. And that's all this is saying. And it just happens to be a very nice little equation that will come up and be useful in the future. All right, so with that, I'm going to pause us and we'll start next class by doing a little bit more Python about how to do matrix multiplications in Python. So if it helps to go and take a look at that on Python before class, please go ahead and do that. But I'm going to give you fair warning that we're going to start next time with some Python. Sound good? Okay. And then given the poll, if the transit strike continues, the vast majority of people voted for continuing online. So we'll go ahead and do that. There is some issues with doing the hybrid in that I don't think the sound is super good on the hybrid option. So unless I have a revolt, I will stick with an online version, unfortunately. But hopefully there will be no transit strike comes Wednesday. So see you either online or in person, given no transit strike on Wednesday. Sound good? Okay, bye. Thank you.
Thank you.
Bye, Luca. Thank you.